Welcome to Philosophy 102, Introduction to Logic. My name is Cecilea Moon, and I am your instructor for this course. This lecture is on Lesson 8. Throughout Lesson 8, we will be covering Chapter 12, Statistical Reasoning, of your text, A Concise Introduction to Logic by Patrick Hurley. We will focus on sections 12.1, Evaluating Statistics, 12.2, Sample, 12.3, The Meaning of Average, 12.4, Dispersion, 12.5, Graphs and Pictograms, and section 12.6, Percentages. The questions that will frame this lesson are: what are statistical arguments and arguments that use statistics? What is a statistic? What is a sample? And how do we evaluate the strength of statistical arguments and arguments that use statistics in terms of the sample being used? What is an average? And how do we evaluate the strength of statistical arguments and arguments that use statistics in terms of the average being used? What is the standard deviation? And how do we evaluate the strength of statistical arguments and arguments that use statistics in terms of the standard deviation of the average being used? And finally, what are some ways in which graphs, statistics, and quantitative information can be misleading? As we discussed, a statistical argument is an argument with the following form. It has as one of its premises a statement that observes that a sample or a percentage of a group or class X has some characteristics or qualities A, B, C, etc. It has as another premise a statement that asserts that some particular thing Y belongs in the group or class X mentioned in the premises. And finally, it has as a conclusion a statement that asserts that the particular thing Y probably also has the characteristics or qualities A, B, C, etc. mentioned in the premises. We can see these features of a statistical argument in our example here. In this example, premise 1 states that 90% of Clemson students love logic. Then the second premise states that Gretchen is a Clemson student. Then the conclusion asserts that Gretchen probably loves logic. In short, you can understand the form of a statistical argument as an argument which moves from an observation about a sample of a group or population in the premises to a conclusion about a particular individual belonging to the group or population. Now note that statistical arguments are different from arguments that simply use statistics. Consider, for example, the three arguments shown below. The first is a strong predictive argument. The argument states as its first premise, Carrie hit a bullseye 9 out of 10 times she took a shot. Then as the conclusion, it asserts that so next time she takes a shot, she will probably hit a bullseye. Notice how the premise cites information about past events and the conclusion makes a prediction. Also notice that this argument uses a statistic in its premises. This does not make the argument into a statistical argument since the form of this argument is not consistent with the form of a statistical argument. The predictive argument moves from an observation about past events in the premises to a conclusion about a future event. However, the strength of this argument will depend on an analysis of the statistic since the statistic is used as a reason in support of the conclusion. The second argument has the form of an inductive generalization. The argument states as its premise 100% of a sample of Clemson students love football. The conclusion asserts so 100% of Clemson students love football. Note that this argument uses a statistic in its premises as well. So the strength of this argument will also depend on the evaluation of the statistic in question. However, again, the argument is not a statistical argument. For the argument to be a statistical argument, the argument must also have the form of a statistical argument, which it does not. This argument argues from an observation about a sample of a group or a population to a conclusion about the entire group or population as a whole. Then third, we have a composition. We haven't actually discussed compositions yet, and we will get into more detail about compositions when we continue on to Lesson 10. However, for now, all you need to understand is that compositions are inductive arguments that argue from observations about a part of a thing in the premises to a conclusion about the whole thing. Furthermore, compositions may use statistics as well, but this does not make them into statistical arguments. However, like other arguments that use statistics, the strength of these arguments will also depend on the evaluation of the statistic in question. Now, when we have a statistical argument or an argument that uses statistics, we want to ensure that the statistic used is reliable, that the statistic is able to support an inference from the premises to the conclusion. So let us now turn to understanding statistics and how they are evaluated when considering the strength of statistical arguments and arguments that use statistics. A statistic is a quantitative piece of information that represents information from a large number of things, or a sample. A sample is a subset of a population, and a population is any group of objects, not just human populations. The statistic gives us information either about a sample of a population or about the population itself. For example, the statement 80% of a sample of Clemson students love football tells us about a sample of a population. And the statement 80% of Clemson students love football tells us about the entire population of Clemson students. Now, it is often the case that the claim about an entire population is often inferred from information about a sample of that population, unless the entire population in question is rather small. When inferences are made about entire populations based on a sample of that population, we want to make sure that the sample is representative in order to ensure that the inference is strong. A representative sample is a sample that accurately reflects the characteristic of that population as a whole. If a population is not representative, we refer to the sample as a biased sample. A biased sample is a sample that is not a representative sample. It does not accurately reflect the characteristics of the population as a whole. This bias in the sample may be due to problems with randomness of sample, sample size, or psychological factors. Any inference from a biased sample will only weakly support an inference about the population that the sample is about. To ensure that a sample is a representative sample and not a biased sample, we want to make sure that the sample is a random sample. A random sample is a sample where every member of the population has an equal chance of getting into the sample. Here is an example of an argument that uses statistics. The argument reads, researchers at the University of Aberdeen's Face Research Laboratory have some news of interest for particularly masculine-looking men. Almost 4,800 women from around the world logged on to the organization's online lab over the past year, viewed 20 pairs of male faces, similar but one slightly more masculine than the other, and expressed their preferences. The Wall Street Journal reports on what the researchers found. They could predict how masculine a woman likes her men based on her nation's World Health Organization statistics for mortality rates, life expectancy, and the impact of communicable disease. In short, women in less healthy countries preferred more masculine men, perhaps for their evolutionary advantages. Testosterone is linked to health. Now, this is an argument that uses statistics, but it is not a statistical argument since it does not have the form of a statistical argument. This is actually in the form of a causal argument since it observes various correlations in the premises that they could predict how masculine a woman likes her men based on her nation's World Health Organization statistics for mortality rates, life expectancy, and the impact of communicable disease, and then draws a conclusion that is making a causal claim that women in less healthy countries preferred more masculine men. Also note that the statistic used here is implied rather than numerically expressed. The statistic is that there is a high degree of correlation among the sample's preferences for masculinity and the World Health Organization statistics for mortality, life expectancy, and impact of communicable disease for their country. Now, given that this argument is in the form of a causal argument, we can perform a logical analysis in order to determine the strength of the argument. This will then tell us if the argument is a causal argument or a false cause. So let us see what we can determine. Note that the sample is 4,800 women from around the world and the population is all women. The sample size used by this group is pretty large, so there is most likely no huge problem with the sample size. However, there may be issues with the representativeness of the sample. This is not a random sample because not every woman had an equal chance of getting into the sample. This reduces the likelihood that the sample is representative of the population. The sample excludes women who do not have access to the internet and this organization's online lab. Thus, although the sample is quite large, this is a weak argument due to the lack of randomness of the sample. Furthermore, there are other things that we can consider besides sample size and representativeness of the sample because this is a causal argument. Such things as more reasonable alternative explanations may also show this to be a weak argument. But we will discuss this further in Lesson 9 when we discuss causal arguments. Other than biased samples, another thing that can weaken a statistical argument or an argument that uses statistics is the amount of sampling error a particular statistic has. A sampling error is the difference between the relative frequency with which some characteristic occurs in a sample and the relative frequency with which the same characteristic occurs in the population. Since a statistic based on a sample of a population is often used to infer conclusions about a population, we want to ensure that the sample population is representative of the population as a whole. So we want to make sure to limit the degree of sampling error that a statistic has. A margin of error represents the amount of sampling error a statistic might have. The larger the margin of error is for a statistic, the higher the amount of sampling error will be for that statistic. Assuming randomness in collecting a sample, the margin of error that a sample has can be limited by the size of the sample. The larger the sample size, the smaller the margin of error. Although the larger the sample size for a given population, the smaller the margin of error, there is a maximum limit for sample sizes. The precision of a sample is not a linear ratio between sample size and population. When the population is very large, the sample size needed for a certain level of precision levels off at a constant figure. Here is a chart that shows you the correlation between sample size and margin of error. You can use this chart to determine how much sampling error a statistic will have based on the size of the sample. By determining the margin of error, you can determine the strength of an argument that uses statistics by considering whether or not the conclusion of an argument takes into consideration the statistic's margin of error. So for example, consider argument 1. It argues that from a poll of a random sample of 9,604 people, 53% said they preferred Jones for governor. And it concludes that 53% of the people prefer Jones for governor. The margin of error based on the sample size used is plus or minus 1%. This means that we can be 95% sure that the actual percentage of people that prefer Jones is between 52% and 54% because the margin of error is plus or minus 1%, which means we can calculate the range of the actual percentage by adding 1% from the statistic drawn and subtracting 1% from the statistic drawn. So if the margin of error gives us a range of 52% to 54%, which includes three discrete numbers, 52, 53, 54, and the conclusion is about 53% of the people preferring Jones, then there is a probability of 1/3 or 33% chance that the conclusion would be correct. The conclusion then is not very probable. Compare this with argument 2. Argument 2 has as its conclusion that between 52% to 54% of the people prefer Jones for governor. This is then a strong argument since the margin of error tells us that we can be 95% certain that between 52 to 54% of the population prefers Jones for governor, and this is exactly what the conclusion states. 95% confidence indicates a pretty high probability. Now, we have spoken a lot about statistics specifically in terms of percentages. Statistics can also be presented in terms of averages rather than percentages. When this is the case, you need to consider information regarding averages. There are three different types of averages that we need to be aware of: the mean, median, and mode. Second, these are statistics as well. They are statistical averages. Third, to understand how to evaluate the strength of arguments that use averages, you need to understand what kind of information the averages do and do not tell you. By doing so, you'll understand what kind of conclusion is strongly supported and what kind of conclusion is weakly supported. And fourth, the most important thing to know about what kind of information the averages do and do not tell you is to understand how they are calculated. As mentioned, there are three types of statistical averages: the mean, median, and mode. The mean is a statistical average that is determined by adding the numerical values in the data concerning the examined objects, then dividing by the number of objects that were measured. The median is a statistical average that is determined by locating the value that separates the entire set of data in half. The mode is a statistical average that is determined by locating the value that occurs the most. Now, here are some examples of how to calculate the mean, median, and mode for a set of values. Note here that the set of values we have is 1, 4, 2, 4, 2, 4, 3, and 4. These are all the values in our set that we will be using to calculate the mean, median, and mode for the set. The mean, median, and mode give us information about the set of values. To calculate the mean, we simply add all the values in the set together and then divide that sum by the total number of values we have in the set. The total of number of values in the set is 8. So we add 1 plus 4 plus 2 plus 4 plus 2 plus 4 plus 3 plus 4, and this gives us the sum of 24. Then we divide the sum by 8, which will give us 3. So 3 is the mean for the set of values we have here. Now to calculate the median, we first want to put the values in our set in numerical order, starting from smallest and moving left to the largest numbers. Then after we put the numbers in numerical order, we want to find the number that lies at the halfway point between all the numbers. A number is at the halfway point if there is the same amount of numbers on either side of that number. If there are an odd number of values in the set, there will only be one number that lies at the halfway point between all the numbers. Only one number will have the amount of numbers on both sides of it. If there is an even number of values in the set, then you take the two numbers that together lie at the halfway point and you get their average. In our example, we have an even number of values. We have a total of 8 values in our set. So we will have to find the average of two numbers that together lie at the halfway point. To find those two numbers, we arrange our values in numerical order from smallest to largest numbers. Then we simply divide our list of numbers in half. Notice that 3 and 4 are the two numbers that together lie at the halfway point between all the numbers. There are 3 numbers to the right of 3, and there are 3 numbers to the left of 4. So now we would average these two numbers in order to get the median. But if we have an odd number of values, we would not need to do so. Since only one number would lie at the halfway point, this would be the median if we had an odd number of values. The average of 3 and 4 is 3 plus 4 divided by 2, which gives us 3.5. So 3.5 is the median for our set of values. Now to calculate the mode, you simply need to find which number occurs the most in the set. The easiest way to do so is to simply put all the values in numerical order first, as you did with calculating the median. Then you simply look at your list to see which number occurs the most. 4 is the number that occurs the most in our set, so 4 is the mode for our set. Now, given that you understand how to calculate the mean, median, and mode of a set of values, let us consider how you can use this information to evaluate the strength of arguments that use statistical averages. In order to understand how to evaluate the strength of arguments that use statistics, you need to understand how these averages are calculated, since that will tell you what kind of information these averages will or will not provide you. Now consider this scenario. Let's say we have two groups, Group A and Group B. Each of these groups is made up of 11 members. So there are a total of 11 individuals in our set for each group. Now let's say I tell you that the mean age of the individuals in each set is 45. What can you tell me about the population of each of the groups based on the average mean? The answer is not much. So the moral here is that the mean alone of any set of numbers does not strongly support any inference about the population. In other words, anytime an argument concludes something about a population based only on the mean of that population, you can bet that it is a weak argument. Now let's say that instead of giving you the average mean of the ages in our two groups, I gave you the median age for each group. The median age for Group A is 76 and the median age for Group B is 46. What can this information tell you about the population of each group? For Group A, you can strongly infer that 50% of the people in that group are younger than 76 and 50% of the people in that group are older than 76. For Group B, you can strongly infer that 50% of the people in that group are younger than 46 and 50% of the people in that group are older than 46. So we can strongly support only inferences about 50% of the group being below or above the median if we are only given the median for a set. Thus, only arguments that conclude this kind of information when only given the median of a set will be a strong argument. For Group A, you can strongly infer that 50% of the individuals are younger than 76, 50% are older than 76, and that there are young children in this group. This is because since half the individuals in this group is older than 76, and we know that the median is 45, we should also know that there needs to be some young children in this group in order to drop the mean average to 45. For Group B, you cannot strongly infer anything about the age of the group except that 50% of the individuals are younger than 46 and 50% of the individuals are older than 46. So the mean and the median together may provide information beyond the mean and the median, but not always. The conclusions that will be strongly supported by both mean and the median together must be considered on a case-by-case basis. Now what about the mode? If I only told you that the mode for Group A is 5 and that the mode for Group B is 47, what can you strongly infer about the population in the set? For Group A, you can infer that there are at least 2 5-year-olds and that there are more 5-year-olds than any other age in the group, but you cannot say exactly how many 5-year-olds there are. For Group B, you can infer that there are at least 2 47-year-olds and that there are more 47-year-olds than any other age in that group, but you cannot say exactly how many 47-year-olds there are. So the mode can strongly support only inferences about there being at least 2 individuals that are equal to the mode and that the number representing the mode is the largest subgroup in the population. What if we were given the average, mean, median, and mode? For Group A, we can strongly infer from the mean and the median that there are young children in this group. We can strongly infer from the mode that at least 2 of these children are 5, and we can strongly infer from the mean, median, and mode that the ages of the individuals are fairly spread out from each other, but we don't know by how much. For Group B, we can strongly infer from the mode that at least 2 of the people in the group are 47 years old, and from the mean, median, and mode, we can strongly infer that the ages of everyone that makes up the group are fairly close together, but we don't know by how much. So the mean, median, and mode can give you more information, including some idea about distribution, but still not that much. So what were the actual facts about our 2 groups and their age numbers? Well, Group A had 2 5-year-olds, 1 4-year-old, 1 3-year-old, 1 2-year-old, 1 76-year-old, 1 77-year-old, 1 79-year-old, 1 80-year-old, and 1 86-year-old. Group B had 1 41-year-old, 1 42-year-old, 2 43-year-olds, 1 44-year-old, 1 46-year-old, 4 47-year-olds, and 1 48-year-old. Now considering this, you can see how accurate our strong conclusions were. I'm not going to go over each of the conclusions we strongly inferred. I will leave this up to you to do so. Besides the mean, median, and mode, another bit of information that may be helpful is a standard deviation of a set of numbers. The standard deviation is a measure of the amount of diversity in a set of numerical values. It tells us how spread out the values in the set are. It is the average of the distance of each number from the mean. Understanding and knowing what the standard deviation is of a set will allow you to strongly infer general information about the diversity among the values in the set. The larger the size of the standard deviation, the larger the diversity. The smaller the size of the standard deviation, the smaller the diversity. Here are some steps for calculating the standard deviation of a set of numbers. Step 1. Calculate the mean. Step 2. Calculate the difference between each value in the set and the mean value. Step 3. Multiply each difference by itself. Square each difference. Step 4. Add the results of the squaring process in Step 3. Step 5. Divide the results of Step 4 by 1 fewer than the number of members in the set for the sample variance, or divide the result of Step 4 by the number of members in the set for the population variance. Then Step 6. Get the square root of the variance, either the population variance or the sample variance, and this will be your standard deviation. So let us calculate the standard deviation of the ages in the 2 groups we worked with. Now we already calculated that the mean for both Group A and Group B was 45. Our next step then is to calculate the difference between each value in a set and the mean. So we want to subtract the mean from each value in the set. This means that for numbers that are smaller than the mean, we will end up with a negative value because we will be taking the small number and then subtracting 45 from it. So for example, in group A, the first value in this set is 5. So we will be subtracting the mean 45 from 5, which will give us negative 40. I went ahead and subtracted the mean 45 from each of the values in both groups. The numbers in red are the results. The numbers in black on the left of the equal sign show you how I obtained each value. Notice how the mean 45 appears on the right of each subtraction sign. This is because in each case I am subtracting the mean 45 from the given value in the set. Our third step is to square each difference we got from performing the previous step, step 2. So we want to take the results that we got from subtracting the mean from each of our values, and we want to multiply that number, the difference, by itself. You might want to use a calculator for this. I went ahead and did this for each group. The numbers in red are the results of the squaring, and the numbers in black that appear on the left of the equal sign show you how each result was obtained. Notice how each number was multiplied by itself. That is what it means to square a number. For step 4, you add the results of the squaring process done in step 3. I went ahead and did this. The numbers in red are the sum of all the numbers we got from the squaring process in step 3. The numbers in black on the left of the equal sign show you how the sum was obtained. Each of the numbers in black on the left of the equal sign is a result we got from the process of squaring the given value in step 3. In step 5, there are 2 possible steps we can take, although your text only provides one. We can divide the result of step 4 by 1 fewer than the number of members in the set. We take this route if we are using a sample as our set of values in order to calculate the standard deviation of an entire population that the sample represents. By taking this route, we will be calculating the sample variance in order to calculate the sample standard deviation. For example, if I want to know what the standard deviation is for ages in the entire population of U.S. citizens, and I use a sample of U.S. citizens to calculate the standard deviation, then I would take the route of first calculating the sample variance in order to calculate the sample standard deviation. Another route we can take is to divide the result of step 4 by the number of values in the set. We would take this route if we are using a total population as our set of values. By taking this route, we would be calculating the population variance in order to calculate the population standard deviation. The difference between the population variance and the sample variance is that the sample variance calculates the variance of a population based on a sample, whereas the population variance uses the entire population itself and not a sample of the population. A population variance will often be used when the population is small, and the sample variance will often be used when the population is very large, and so information about the entire population is difficult to obtain. The reason why the sample variance divides the sum from step 3 by 1 minus the number of values in the set is to take into account errors that may have been introduced by using a sample to calculate the variance of a population rather than the population itself. It's a way to be conservative about the standard deviation, since the standard deviation, as the sample standard deviation, is based on a sample and not the actual population. So there may be some inaccuracies introduced which we would want to correct for by being conservative about the standard deviation. Since we are dealing with total populations here, in other words, each of our groups represents a unique population that we want information about rather than a sample of a population, we will divide the results by the number of values in the set in order to get the population variance. The results obtained from dividing the sum from step 3 by the total number of values in each set appear in red, and the numbers in black show you how this result was obtained. Finally, in step 6, we take the square root of the results from step 5. If the sample variance was used, this will give you the sample standard deviation. If the population variance was used, this will give you the population standard deviation. Both standard deviations reflect information about the population in question. The only difference is that the sample standard deviation reflects information about the total population based on sample rather than the total population itself. Since we initially calculated the population variance, when we obtain the square root of this number, we end up with the population standard deviation. This number, as with the sample standard deviation, tells us the average distance from the mean of all the numbers in the set of the population. This then tells us how closely the numbers are grouped together in the set of the population, or how far apart they are. In other words, they tell us if the values in the set or the population are very diverse or not. See how the population standard deviation for group A is very large. It is 36.44. This tells us that on average, the numbers in the set are about 36 points away from the mean of 45, which then tells us that there is a lot of diversity in the set, that the numbers in the set are not all very close to each other. For group B, the population standard deviation is 2.335. This is a very low number. This tells us that on average, the numbers in the set are about 2.33 points away from the mean of 45, which tells us that there is very little diversity in the set, that the numbers in the set are very close to each other. Let us now consider how graphs, percentages, and quantitative information can be misleading. I present here only some of the things mentioned in your text, as well as some information not included in your text. The information that I focus on here is what I consider to be important enough to emphasize. However, please note that the information presented in the text, but not covered in this lecture, is also important. If you have any questions about the material or any other material presented, please let me know. Now, there are two important ways that graphs can be misleading. First, they can mislead by not providing a scale for the x-axis and y-axis. Also, they can mislead by chopping off the bottom of the graph or altering the scale of the axes. I will discuss these in more detail in a little bit. Two important ways percentages can mislead is by failing to state or provide the base of the percentage, and by using sleight of hand tricks with the base. The base tells us what the percentage is a percentage of. A sleight of hand trick with the base involves misrepresenting what the true or accurate base is. I will also further discuss this in a little bit. Finally, one important thing to consider about quantitative information is that quantitative information may be interpreted in different ways compared to qualitative information. I will further discuss this as well. As mentioned, one way that a graph can mislead is by failing to give a scale for the x-axis and the y-axis of the graph. Notice how the above graph in figure 12.6 conveys practically no useful information. This is because there is no scale provided on either the x-axis or the y-axis. Because of this, we do not know what the graph represents in terms of vertical or horizontal movement. So not much can be inferred from this kind of graph, and any conclusion drawn from such information will be weakly supported. Now here is a graph that accurately depicts information about a particular company. According to this graph, the company in question had increased their profits from $8 million to $10 million over a span of 4 quarters. From this information, we can strongly infer conclusions that are mathematically implied by the information depicted in the graph. For example, we can strongly infer that the company experienced a 25% increase in profits over 4 quarters. This 25% increase was calculated by first calculating the increase in the profits by subtracting the starting amount of $8 million from the ending amount of $10 million. Doing so gave us an increase in profits of $2 million. Then we calculated that $2 million was 25% of the base of $8 million by doing a little algebra. Now, a second way that a graph can mislead is by cutting off the bottom of the graph and changing the scale. Consider this graph here. This graph actually depicts the same information as the previous graph. However, see how the bottom of the graph was cut off compared to the previous graph. The previous graph began at 0 on the x and y axes. In this graph, you can see that the y-axis begins at 8. Furthermore, the scale has been changed. Notice how the scale of this graph only depicts the range from $8 million to $10 million. Now, although this graph is accurate, because of the alterations made, it can be used to visually mislead people to draw weak conclusions. For example, one might conclude that the profits of this company significantly increased over 4 quarters, and the graph may seem to strongly support this conclusion. However, if by significantly increased the author is suggesting something like doubled, then this would be a weak argument based on the information depicted. So you should be very careful with arguments that use graphs. Make sure you pay close attention to what information is actually being depicted by the graph. You also need to be careful with arguments that rely on the following kinds of claims. One claim states that Cecilea has 20% fewer calories, and the other claim states that the price of CompuTrick computers has been reduced by 15%. Note how neither of these claims tell you what the base of the percentage is. 20% of what? 15% of what? Without information about what the base of the percentage is, such claims are basically useless. They don't really convey any useful information at all, so any argument that draws a conclusion from such claims will be weak. Another shady way of using percentages is by using a sleight of hand trick with the base of the percentage. This is done by changing the base to an inaccurate base in order to support an alternative conclusion. For example, consider this scenario. Let's say that a fundraiser was hired to increase endowment funds from $15 million to $20 million. And let's say that the fundraiser was able to increase funds from $15 million to $16 million. This means that the fundraiser was 20% successful since only 20% of the goal, which was an increase of $5 million, was actually achieved. However, the fundraiser might try a sleight of hand trick by changing the base of the percentages. Instead of using $5 million as the base for the goal and $1 million as the base for the amount increased, the fundraiser might attempt to use $20 million as the base for the goal and $16 million as the base of the increase. This would then suggest that the fundraiser was 80% successful, which is actually inaccurate and so would be weakly supported by the actual facts. So make sure you pay attention to the bases that are being used to make sure that the argument does not rely on inaccurate information in order to draw inaccurate conclusions. Finally, graphs, percentages, and statistics deal primarily with quantitative information, information that is given in numerical values. However, such information often lends itself to interpretations that are different from qualitative information that is given in terms of subjective qualities. For example, consider the claim that the latest album by the Green Biscuits is #1 in sales this year. This provides quantitative information that can be expressed in numbers. Now consider the statement, the latest album by the Green Biscuits is the best album this year. This provides qualitative information that is given in terms of subjective qualities. Now we can strongly infer the second statement from the first only if best was explicitly defined as being #1 in sales. However, without such explicit definitions, arguing from a premise like the first statement to a conclusion like the second statement may be weak. This is because best might be given a completely different interpretation, such as being the most critically acclaimed rather than having the highest sales, and these two may not be well correlated. So when evaluating arguments that use quantitative information to draw qualitative conclusions, make sure you consider what kind of qualitative claims are being concluded from quantitative claims. If the qualitative claims are strongly implied by the quantitative claims, then the argument is strong. If not, then the argument is weak. This marks the end of Lesson 8 online lecture. I will see you all next time for Lesson 9.